like that. So very short lecture, I have just 3 slides. So I just want to like highlight one particular nuance that perhaps you have not yet appreciated. So in particular, I don't know, maybe you should quickly define before I do what you think these 3 words mean to your neighbor. Just go ahead and turn to your neighbor right now and like talk to your neighbor and say what the difference you think is between those 3 words. This isn't the first time we've had this like discussion about the difference between those, so I'm sure what you just said was fully correct. Good job. Okay, but I just want to make sure like you've thought a little bit about this. I want to make sure you're hearing that because when we ask those questions, we specifically mean one thing or another and not the other. Okay, so just to be clear, I think those things can be easily confused. So let's look at the warm-up again, and if we really do have a position function derived by Caden, it's S of t or whatever, and we'll just assume he's right. We could ask a couple different questions about this motion, if it's some particle in motion. We could ask something like this: what is the velocity of the particle when its acceleration is at a maximum? There's like a lot going on in that question, even though it's easy to ask, right? So you might take a look at the acceleration function, which has this as its derivative, and then find where it's at a maximum. That requires setting its derivative equal to 0, or maybe looking at the graph and finding this place right here. I'm looking right now at a graph of A prime, so I'm looking for the 0 for that graph. And is that a maximum? Just remind me why that is a maximum. Why is that? For A. Yeah, because the derivative A prime goes from positive to negative, yeah. So that point right there, whatever it is, 1.496 seconds, or whatever units we're using, does correspond for A of t to a maximum value for A. Now, of course, that isn't what the question is. It also then says, what's the velocity? So we can go ahead and plug that value back into the original equation as well, right? Into the original velocity function. Do we have a velocity function from the previous slide? I don't have that written up here, but we should do that maybe. V of 1.495 and 9, etc. Actually, I might do that on the calculator if we have it. So we'll actually maybe type that in. Did you write down the velocity function? Maybe I'll ask. It must be the antiderivative of 2 antiderivative of that. What was it? Someone hand it to me.
3 to the t minus
3 to the t? E to the t?
minus t to the 4 over 5 plus 3.
Can someone else verify that that's correct? Okay. Yeah. All right, so let's, yeah, we can actually do this then. Let me pull up my calculator, and I think we have the time to type it in real quick. And I kind of want to get this actual value in all of its glory. You try using the big calculator. I got 4t cubed. Looks like 0 to 2 will be a good deal. Sure. Whatever. Doesn't matter. I'm just trying to get this one point here. Oops. Something like that. All right, and then if I go back here, right now that's the value we're looking for, right? So 3, actually it might be easier to put this in y2 just for the time being. We have 3 e to the x minus plus 3. Actually, what I meant is x still that? I don't know. That should be, I think, but so there's, well, I'll write down 14.892. Right. Let's assume everything was in meters per second or something. That'll be in meters per second then too, the velocity. Acceleration will be in meters per second squared, etc. Okay. I think this is a question we've asked you earlier in the year, but I thought we'd ask it again while we're in the context of this motion stuff right now. Do you remember how we answered that question? How do we make the determination whether something is speeding up or slowing down? What does that mean? Yeah.
Whether its acceleration is positive or negative.
Okay, so that is definitely of interest to me. So do I have the? I don't actually have the acceleration function. This is going to be confusing. I'm going to put it in y3. What is it? It's 3 e to the x minus, come on now, x to the 4th. Is that the, just that, right? Is the acceleration function? That's the thing I gave you as the warm-up. Great. All right, so what was your name again? Sorry. Kevin says, let's just figure out whether the acceleration, which I put in y3 just now, I know it's confusing, but at 6.5 is what I guess I said, is positive or negative. Eventually I'll be able to use this calculator. So it looks like it's positive, so therefore it's speeding up. Or is that the whole story? Does anyone have a little more nuance to this? Keep in mind that acceleration, if I'm even when I'm slowing a car down, for example, I am actually exhibiting an acceleration, which is maybe in a different direction than you anticipated, right? Maybe in some sense there's no such thing as deceleration. There's just acceleration in one direction or another. So maybe acceleration doesn't tell the whole story, though it's important. Like I'm glad, like that calculation we just did is not lost on us. That's important, yeah. Yeah, does this ring a bell? I know all of you have heard this before, but we need to be accelerating in the same direction we're traveling, right? So we need acceleration and the velocity to both be positive, or both negative would be fine too, actually. So I want to make sure you're hearing that. So let's also ask that. How do we ask that? Which one did I put velocity in? I actually don't know. It's y2, is that right? Okay. So this is the big moment. This is huge. All right, so what is happening here then? Yeah, it's actually slowing down, right? Because we're moving. If we're talking about, I'm not sure what the context is here, but maybe we're talking about a particle moving left and right on the x-axis or something like that. Then that means we're moving to the left, but accelerating to the right. That means we're slowing down, right? Again, I think those are questions that we've asked before. Oh, there we go. Whatever. Aha. Did I just do that? Good. Okay. I forgot that was coming up. Okay. Now I'm finally ready to answer the questions we started with here. Give an equation for the position of a particle that moves along the x-axis. This is a new problem now, with that as its velocity. This is not maybe the most important part of this problem. You want to call it x of t? Yeah, I guess x of 0 we said there. So x of t will be equal to, well, that's convenient, isn't it? It's just t cubed minus t squared minus t plus something, plus a constant, which in this particular case looks like if we plug in 0 and then we have a 3 here, then that will make that happen. It's not as obvious. It's nice with polynomials, isn't it? Because if you plug 0 into a polynomial, you'll get just the constant term. So that's a nice property of polynomials that we can always be taking advantage of. Great. Did I just do it? Find the position of a particle such that that was not, like I said, that's kind of a little bit like what we did yesterday. That's not the interesting part of. So what's the position of the particle at t equals 3, and then I'm going to follow that with the other two questions of the day, and that's what's its displacement over the interval 0 to 3, and how much distance did it cover during that interval? I'd like to ask all three of those questions to make sure that we're feeling good about that. So what is the position of the particle at t equals 3? One way to do that would be to plug it into the equation and get an answer. So someone do that, if you will. Another way to do it would be to start with the initial position and then add the amount that it's gone, right? And how much did it go? Well, it went, well, how do you calculate how far something went if you have the velocity function available to you? So now we've actually figured out what this function is, we can just write it down. We can actually plug it in. But you could also use what recent tool that we've been harping on a lot. Yeah, we could actually calculate the integral from 0 to 3 of v of t dt. Right, and both this and this is of course just 3. 3, right, your initial position, plus the amount it changed, right, from 0 to 3. Either one of these should give the same answer. This is, of course, maybe natural. If you already have the position function, you can just plug in 3. Doesn't someone have it? It's actually, we could probably do it in our head, huh? What does it come out to be? 27 minus. Is it 18 exactly? Okay, yeah. Call it meters, maybe. I don't know what the units are in this problem. But both calculations would be fine, right? I hope you understand the form of this expression and why that computes what we needed to. Okay, so what about the displacement? What is that going to be? How do we compute how far it went over that interval? Again, perhaps two ways to do this. You talked about it with your neighbor earlier, so what did you say? What is displacement for a particle? How does that differ than just asking, like, is the answer 18 meters? No. Well, what is it then? How do you calculate it? The displacement. No. Yeah, so that, I guess, right? Which I heard someone saying is 18 meters minus 3 meters, so what does that come out to? 15 meters. And then just to be clear, what's another way to do it? Did we just talk about this a second ago? You can also compute this integral, yes? Please explain why those are the same thing. Why are these the same thing? Yeah?
Fundamental theorem of calculus.
The fundamental theorem of calculus says so, right? What is x with its relationship to v? Oh yeah, that's right. It's an antiderivative of v, right? So this is just the fundamental theorem of calculus part 2 or whatever we call it, right? Okay. Little f, big F we sometimes used also, right? And then what about the distance traveled by the particle over that interval? Again, a couple different ways to come at this, but I think you understand what we're trying to calculate. The distance covered, which could have been, maybe you moved back and forth, who knows, all over the place. We haven't really talked about that part yet. So give me one way at least to calculate that successfully. How did you get at that? Good. Yeah, so one way would be to take this and, now, yeah, to be clear, I mean, you don't take the absolute value afterward. You remember doing this earlier, maybe. And do that. And tell me what you get. You can run fn on that if you still have the velocity function available, or whatever it was. What is the other way to do that? What is the other way to do that? Besides using an absolute value. Is there a way to do it without resorting to absolute value? I mean, because if we use absolute value, we really do just need to feed it to the calculator, maybe, right? Which is fine. But is there another way in? Like, I don't know how to compute that integral by hand based on absolute value. Yeah, go ahead. Yeah, if such a point exists, I think maybe that happens here, just because otherwise it wouldn't be an interesting question. But yeah, remember that, you might need to break up the integral, find out where it goes below the x-axis, and then just integrate that and treat it as positive. Let's do this one more sheet for homework. I think that'll be sufficient. Okay, did everyone get it? Yes, how is there? Anybody still new? Alright. One more, sorry. Here we go. Alright. Have a great day, guys.